Welcome back to our lecture. Our next topic is going to be virtual private clouds, or VPCs. A VPC is basically a logical network that you can create within an AWS region. And its primary purpose is to allow us to partition resources within a region. You can think of a VPC as being sort of like a private cloud-based data center, in that you can create multiple VPCs, and in each VPC you can specify a network and you can specify resources that live within that particular VPC. So think of VPCs as being sort of like a container, a way to containerize our resources within a region. The benefit of a VPC is that it allows you to build secure application architectures and to partition applications within a broader organization. For example, if your organization had multiple teams, multiple divisions, then each team might have its own individual VPC, and within that VPC, each team would have its resources. And then that allows each team to kind of clearly control who has access to the resources and how those resources may be accessed. Now, VPCs are one of the most challenging topics that you will work with in AWS, especially if you don't have much of a networking background. But don't worry, even though they're a little bit challenging to understand at first, we'll walk through all of the basic things that you need to know about VPCs. And understanding VPCs is really, really important, especially in this course, because many of the other services that we will work with depend on VPCs. So here's a basic use case for a VPC. We have an AWS region, and within that region, we have defined a VPC. That VPC has two subnets defined within it, and one of the subnets has some public web servers, and the other subnet has something like a database. And with this sort of configuration, what we can do is we can allow customers from the internet to access our public web servers, but we then protect our database server from access via the internet by placing it into a private subnet. You can see how this VPC architecture is allowing us to sort of carve up and create different subnets, and then place resources into those subnets, and then define security group rules which allow either public access to those resources or private access to those resources. When you start working with VPCs, one of the things to understand is that you can create multiple VPCs within any given region. And when you create each VPC, the VPC has its own privately routable network block. So, for example, in this diagram, you see that I have a region where I have defined three different VPCs, VPC A, B, and C. And each VPC is associated with a network block or a network range. This represents a usable set of IP addresses that I can use within that VPC. Think of this as being like your internet network or your local network that you're defining for the VPC. If you were to configure a router in your home, then you would set up a private network address block associated with the router and all of the other devices within your home. The same thing is true of your business. Like if you're working in a business office, then all of the internal devices within that office would have an internal IP address, which is associated with some sort of internal network block. So each VPC we define within our region will have its own internal network block as well. And you can see in this diagram that VPC B and VPC C both have the same network block assigned, this 10.0.0.0/16. This is called a CEDAR address or CIDR address, which is a sort of a shorthand way of describing a network block. Basically, it's describing the network address and the subnet associated with it. And based on those two components, we can determine the set of IP addresses that are usable within that particular network block. So because each VPC is its own sort of self-contained thing, it's perfectly acceptable to set up multiple VPCs in the same region that have the same network blocks. That doesn't cause any kind of conflict because they're completely separate, partitioned containers. Now, in reality, if you're working for a large organization that has many VPCs, generally each VPC will have its own unique network block, and they won't be sharing the same network block, or they won't have sort of overlapping network blocks, and that's for peering purposes, which we will discuss later in the lecture. And another thing to note about private IPs, I don't get real deep into networking in this particular course, and my assumption is that you have some basic level of network knowledge before taking this course. But I wanted to make sure that we're all on the same page in understanding how to assign network blocks to VPCs. When you set up a network block for a VPC, you have to specify a private IP address range. And so what's important about understanding private IP addresses? Well, private IP addresses represent addresses which are IP addresses which are not publicly routable on the internet, meaning that if you have a device that's assigned an IP address from one of these private IP address ranges, that device is not able to communicate with other devices on the internet. Internet routers will refuse to route traffic for devices that have these IP addresses. So these IP addresses are only usable internally. They're only usable within our home or our office local area network, and they're usable within VPCs because the internal network within a VPC is like the internal network within our office or home. It's a kind of a local area network. But it's important to know that if I have something like an EC2 instance and it has a private IP address, and that's the only address it has, that instance will not, at least not on its own, will not be able to route traffic on the internet because private IP addresses are not routable. So we have a VPC that we create within our region, and we assign a network block to that VPC. The next step is to then partition that network block into one or more subnets. And every VPC has to have at least one subnet in it. And generally, our VPCs will have more than one subnet, but they must have at least one. So each subnet then is going to utilize part of that VPC's network address block. And the subnet, each subnet will have its own network block that is kind of a subset of IP addresses from the general VPC network block. Each subnet that you create is also going to be associated with one availability zone. And a subnet lives within an availability zone. A subnet cannot span multiple availability zones. You can see in this diagram that subnet 1 is associated with availability zone A. So it lives in availability zone A. Subnet 2 lives in availability zone B. It's not possible to create a subnet which would live in both availability zone A and availability zone B. That is not possible. Each subnet can only live within a single availability zone. Very, very important thing to remember. So if we have a VPC that we create in a region and we want to create resources that are going to live within the VPC and live within multiple availability zones, then that tells you that you need to create multiple subnets as well, because something like an EC2 instance is going to be associated with a subnet within a particular availability zone within a particular VPC. One other thing to note is that each subnet that you create within the VPC is going to be associated with one routing table. And it's possible for multiple subnets to share the same routing table. What is the routing table? Well, the routing table describes a set of rules that determines how data is going to be routed within the VPC. So the routing table will describe where traffic is going to be routed once it leaves something like an EC2 instance. And we'll see some examples of how that works here in a bit. But what's important is that each subnet is associated with one route table, and multiple subnets may share the same route table. Multiple subnets, each subnet could have its own routing table. That'd be perfectly fine as well. But they can share a routing table as well. They can only have one routing table, however. I want to do a quick segue and talk about IP addressing within VPCs and how this is related to EC2 instances. Now, we've been working with EC2 instances a bit already, and you have been accessing these EC2 instances remotely via the internet, but we haven't really talked about IP addressing yet. Well, so when you create each EC2 instance, every EC2 instance is going to be given a private IP address. And that private IP address is going to come from the IP address block, which is associated with the VPC. Every EC2 instance you launch is going to be launched within a particular VPC. And remember, the VPC is partitioned into one or more subnets. And so that EC2 instance you launch is actually going to be associated with a subnet within a particular VPC. And each subnet has its own set of network blocks that represent a subset of the network block that's associated with the VPC. So long story short, you launch an EC2 instance It's associated with a particular subnet within a VPC, and that EC2 instance is going to be given automatically a private IP address from that subnet network block. It's also possible, depending on how you configure the subnet, it's possible that the EC2 instance you launch may also have a dynamically assigned public IP address. Remember the difference between private IP addresses and public. Private IP addresses come from those specific address ranges which are not routable addresses on the internet. So any IP address that starts with a 10, for example, is not routable on the internet. That's a private IP address. Public IP addresses, on the other hand, are routable on the internet. Any device that's on the internet that has a public IP address and is allowing access, either it's not being blocked by a firewall or security group, that you will be able to route data to that device. So far, when we have been launching EC2 instances into our accounts and our VPCs, those instances have had public IP addresses. And that's because the subnets within those VPCs that we have been using will automatically assign a public IP address. Now, when you launch an EC2 instance, it is going to be given a private IP address. And it may be given a public IP address. And that public IP address is going to be dynamically assigned by AWS from a large general pool of public IP addresses. If you were to stop that EC2 instance, then that public IP address is going to be given back to AWS. If you restart that instance again, start it back up, it will then be given a new public IP address. The key point here is that dynamic public IP address can change over time as you start and stop that EC2 instance. The private IP address will remain the same. If you stop the instance and start it again, it will still have the same private IP address, but the public one can change every single time the instance starts. Well, there might be times where you want to associate a persistent public IP address, a permanent IP address, with an EC2 instance. And you can do that using what is called an elastic IP. And the elastic IP is a permanent IP address, a public IP address that is associated with an EC2 instance. And if you were to stop or restart the EC2 instance, its elastic IP address would not change. It would stay the same forever. And there's sort of a two-step process with it, with doing this. The first is you would provision a new elastic IP address, and then you would assign that elastic IP address to an EC2 instance. IP addresses, as it turns out, are sort of like in short supply. And so if you were to provision an elastic IP address and not associate it with an EC2 instance, in other words, you're just sort of like keeping it around, you've sort of tied up that IP address so nobody else can use it. If that's the case, then AWS will charge you a small monthly fee for every elastic IP address that is not allocated to an instance. The bottom line is that if you have provisioned elastic IP addresses, you want to make sure you're actually using them and you're associating them with running EC2 instances. Otherwise, you're going to going to incur a small monthly fee. So you have created a VPC. It's got one or more subnets in it. You launch an EC2 instance into a subnet in the VPC, and that EC2 instance has a public IP address. Now, in order to actually communicate with the internet, your VPC needs to be connected to the internet. It has to have a way to route traffic to and from the internet. And it does that using a resource called an NAT Gateway. So in order to sort of attach your VPC to the internet, it has to have an NAT Gateway configured. And a VPC can have only one NAT Gateway. There's never a scenario where you would configure multiple NAT gateways. That's not allowed by AWS. It only allows you to configure one NAT gateway. And this is a managed service. So this isn't like an EC2 instance or something that's, that you have to pay for. There's no additional fee for using an NAT gateway. And the NAT Gateway is what allows your EC2 instance to communicate with the internet. And it's what allows you to remotely communicate with an EC2 instance. In order to access that EC2 instance from the internet, there must be two things in place. One is the VPC must have an NAT Gateway. And second, that EC2 instance you have provisioned must have a public IP address. And there's actually a third thing, which I'll talk about here next, which is dealing with the routing tables. The subnet must be actually routing traffic out to the internet through the NAT Gateway. But in terms of this scenario we're talking about here, you just keep in mind that you need to have an NAT Gateway attached to the VPC, and the EC2 instance must have a public IP address. If the VPC had an NAT Gateway and you had an EC2 instance that only had a private IP address, that EC2 instance would not be able to communicate with the internet, because private IP addresses cannot route traffic on the internet. It's simply not possible. Well, so what if I have an EC2 instance which has a private IP address and it doesn't have a public IP address. It has a private IP address. My VPC has an NAT Gateway. Yet I want to allow that EC2 instance to be able to communicate with the internet. How would I do that? Well, the EC2 instance isn't going to be able to communicate with the internet on its own. The EC2 instance needs some help in order to communicate with the internet. And it can get that help from something called a NAT Gateway, which is a managed service offered by AWS. A NAT Gateway is a resource which will run within our VPC, and it will allow private servers to be able to communicate out to the internet. Why would you want a private server to be able to communicate out to the internet? Well, maybe that private server needs to be able to download security patches from the internet. Maybe it needs to be able to download Ubuntu or Amazon Linux updates. Maybe it needs to be able to communicate with public API endpoints. So there are a variety of reasons why a private server might need to be able to communicate out to the internet. But remember, because it has a private IP address, it can't do that on its own. It can do that, though, by proxying the request through a NAT gateway. A NAT gateway then sort of serves like a router for the private server. A private server is going to, instead of communicating out to the internet through the internet gateway, the private server is going to send its internet bound traffic through the NAT gateway. And then the NAT gateway will send the traffic through the internet gateway and out to some other internet device. And here's where routing tables can come into play. I'm going to go back to the previous slide where we talked about internet gateways. And here you see a diagram where we have a VPC set up within our account. That VPC has a network address block of 10.0.0.0/16. And then the VPC has two subnets configured, a public subnet and a private subnet. The public subnet has an address block of 10.0.0.0/24, and the private subnet has a network of 10.0.1.0/24. So these are our /24, or sometimes we call them Class C network blocks. And each of these subnets has its own set of private IP addresses that it will allocate to EC2 instances that are associated with the respective subnet. Remember I said that each subnet is associated with a routing table. It has to be each subnet has to be associated with one routing table, and they may share the same routing table. That's totally acceptable. In this case, we have set up. In this case we have each subnet is associated with a particular routing table. The public subnet is associated with a custom route table. And this routing table has two routes in it that describe how to route network traffic. The first route says that any traffic which is destined for this network block, 10.0.0.0/16, should be handled locally, should use a local target. This 10.0.0.0/16 network block is the same network block associated with the VPC. In other words, this routing table is saying that any traffic that is destined for a resource that's within the VPC should just be routed locally within the VPC. That's all that first rule is saying. The second rule is saying that any traffic which is destined for 0.0.0/0, this represents everything, basically, everything else. All of that traffic should be targeted and routed to the internet gateway. So the first rule says any traffic which is destined for a resource within the VPC network, then just route it locally. Otherwise, any other traffic should be routed out through the internet gateway. and this is what we call our public subnet. This is where we are hosting our web servers. This is where we might also have a NAT gateway if we configure one. I'm not going to talk about the NAT gateway for now. In our private subnet is also associated with a route table. And this is what we call the main route table. And I'll distinguish, what that means when we look at the hands-on segment. But this route table has a route which is very similar to the public one, in which that says that any traffic which is destined for a resource within the VPC should just be routed locally within the local network. And in this case, any traffic which is destined for the internet, instead of trying to route that traffic through the internet gateway, we're going to try to route it through a NAT. I'll go back to our NAT gateway slide, and you can see in this diagram where we have our NAT gateway, and same thing. Our public subnet, we're routing our traffic within the VPC locally. We're routing traffic out to the internet through the internet gateway. In our private subnet, where we might have something like our database servers, we're going to route traffic. Local traffic is just going to be routed locally within the VPC. And our internet-based traffic is going to be routed out through the NAT gateway. And then the NAT gateway will, because it lives in the public subnet, will route traffic that's destined to the internet through the internet gateway. Now, there are a couple things to think about here. One is that the NAT gateway, in order for the NAT gateway to route traffic out to the internet, the NAT gateway must be in a public subnet. It must be in a subnet which is able to route traffic out through the internet gateway. And the NAT gateway must have a public IP address, because remember, only resources with public IP addresses are able to route traffic through the internet. When we create a NAT gateway, we actually will first create an elastic IP and then associate that elastic IP with the NAT gateway so that the NAT gateway has a public IP address. NAT gateways are managed services. Now, under the hood, they're probably are just very specialized EC2 instances that are being managed by AWS, but we have no access to a NAT gateway. We can't shell into the NAT gateway or configure it in any way. It's a completely managed service, and we pay for NAT gateways on an hourly basis. The other thing that you need to keep in mind is that NAT gateways will allow private EC2 instances to communicate out to the internet. But if you are like an internet user or customer, you cannot access a private instance from the internet through a NAT gateway. The NAT gateway only will allow the communication outbound. It will not allow you to route incoming traffic that's destined for that database server, which is a good security mechanism, right? You wouldn't want people to be able to access your private database servers by just simply initiating requests to NAT gateways. The NAT gateway will not forward that request that it receives from you to a private EC2 instance. A couple other things I want to cover related to VPCs. You can securely connect a VPC to something like a corporate network using what's called a virtual private gateway. A virtual private gateway is a resource that you attach to your VPC and allows you to create a VPN connection to a gateway within your office network. VPN is a virtual private network, and basically it kind of allows you to tie your corporate network directly into the VPC network so that you can route traffic from your corporate network directly to your VPC and vice versa. The VPN sets up a secure tunnel between your corporate local area network and the VPC network running in the cloud. Very, very useful sort of service. We've talked about security groups in the past. Security groups are a way to specify what types of data, traffic, and communications are allowed incoming and outgoing from your EC2 instances and from your various resources like ELB, like your elastic load balancers and NAT gateways and so on. You can also filter traffic at a network level within a VPC using an access control list. Remember, when you set up a security group, you associate EC2 instances with one or more security groups. So it's kind of like an association-based firewall system. An access control list is like a firewall for your individual subnets within your VPC. And the access control list allows you to filter network traffic before it ever reaches your security groups. These access control lists are stateless, which is different than our security groups. Our security groups are stateful. If you recall, in terms of setting up a security group, if you allow something like port 80 traffic incoming into your security group, then the corresponding response to those incoming web requests are going to be allowed by default. If you make a request to a web server and that web server is allowing traffic on port 80 incoming, then any request from that web server that goes out in response to that incoming request is going to be automatically allowed. That's what we call stateful. Access control lists are stateless, meaning that you have to explicitly specify what network traffic is going to be allowed incoming and outgoing from a subnet. If you allow incoming traffic on port 80 in the subnet, and if you want the web server in that subnet to be able to respond to a request on port 80, then you also need to explicitly allow outgoing traffic on port 80. By default, the access control lists that are configured on subnets that you create will allow all ingress and egress data. That's the default. In other words, there is really no access list restriction on data traffic for subnets that you create. Once you start creating rules, however, for an access control list, when you create a new rule for the ACL, then the ACL will deny all traffic unless it is explicitly allowed. So it sort of switches mode from allowing all traffic to only allowing the traffic that is explicitly specified by the rules that you create in the ACL. Here's a diagram that kind of shows you how ACLs and subnets and security groups fit together. Picture traffic coming from the internet through the NAT Gateway. It's going to hit a VPC router, which will look at your routing tables to determine how to route traffic within your VPC. It's going to determine which subnet it should route that traffic to. The subnet, each subnet has its own network ACL, its own network access control list, which is going to determine what traffic, what data can go in and out of that particular subnet. And remember, by default, it's going to allow all traffic in and out. There's no restrictions in place. But if you have a rule or set of rules that you create for the ACL for that subnet, then the traffic is going to be filtered right away before it ever goes into the subnet and is sent to instances. If the network ACL allows traffic into the subnet, then before that traffic, before that communications reach the instance, the communications are going to be filtered by the security groups. So you can see that the network ACL is the first level of filtering that will take place. It's sort of the first security layer that might be blocking communications to your EC2 instance. And once the communications pass the network ACL, then they have to make their way through the security group rules before actually reaching the EC2 instance. When we've been creating EC2 instances within our VPC so far, those EC2 instances have been using what we call the default tenancy option. And there are multiple tenancy options which are available to us. The default tenancy option says that our EC2 instances will run on shared hardware. In other words, our EC2 instances will share the same physical hardware hosts as other customers' EC2 instances. There may be cases where we want our instances to run on single tenant hardware, which is hardware that is dedicated to our organization. Our organization is the only organization which is able to launch EC2 instances on that particular hardware. And the key benefit here is that with dedicated hardware, you might be able to fulfill some compliance requirement or security requirement that your organization has. The third option is to run an EC2 instance on a dedicated host, meaning that it's actually dedicated to a specific EC2 instance. You wouldn't have multiple EC2 instances running on the same host. Each host would have its own dedicated EC2 instance running on it. The single tenant requirements might help you meet some compliance needs, but the thing to keep in mind is that it can be much more expensive. You're going to pay at least $2,000 a month for a region fee in order to deploy dedicated instances. So it can add up very, very quickly. When you set up your account, you can create multiple VPCs within that account. Or you might even have multiple accounts, each of which has its own set of VPCs. It's possible to route traffic between those VPCs located in different regions and different accounts. And you can route traffic between VPCs using a configuration called VPC Peering. And this is really useful. This is something that in practice we do all of the time. We might have different applications and different services running in different VPCs. We may want those services to be able to communicate with one another using private network routing. And the only way to do that is by setting up a VPC peering connection between those VPCs. The key thing to keep in mind when setting up VPC peering is that the way you route traffic through VPCs is the traffic has to be routed directly from one VPC to another. It's not possible to configure what we call transitive routing. So in this diagram, you see a set of VPCs where VPC A is in the middle, and I have VPC C and VPC F that are both connected to VPC A. It's not possible to route traffic directly from VPC C to VPC F, even though these two VPCs are connected to a common VPC A. Not possible to transitively route traffic from between these two separate VPCs. And that's because those VPCs are not directly connected to one another. You can only route traffic between VPCs which are directly connected to one another. If I did need to route traffic between, say, VPC C and VPC B or G or E or some other one, well, what I would have to do is send that traffic to a resource in VPC A first, and then that resource would then essentially proxy the traffic, or it would use some other mechanism to push that traffic out to a resource in one of the other VPCs. And so if you were to set up multiple VPCs and you needed to get data from one VPC to another VPC, you might set up this sort of star topology in order to support that particular use case. One last thing I'll mention about VPCs is that so far when you have been launching EC2 instances in this course, you have been launching those instances into what we call the default VPC. Every AWS account has a default VPC set up in each AWS region. And that's there just for convenience purposes. It allows you, especially as a new AWS customer, to quickly spin up new EC2 instances without having to really understand how VPCs work. And each default VPC has an internet gateway set up, and it has a set of subnets that will route the public traffic through the internet gateway. And every subnet that's set up within the default VPC is essentially a public subnet. So it will automatically assign public IP addresses to new EC2 instances that you launch. And again, this is all done for convenience purposes. It's to make it easy for you as a new customer to onboard AWS and begin immediately launching EC2 instances. And while the default VPC, I think, is great for an initial onboarding experience and as an initial learning tool, the default VPC is not something that you should use in a production setting. It's not something you would use when you're configuring AWS for your organization. In fact, I would either disable the default VPC or potentially even delete it altogether if I was in a corporate sort of setting, because there are the default VPC is not configured appropriately from a security standpoint for use for your business sort of resources.